Welcome to this explainer. Today, we're going to completely decode the binary tree symmetry problem, giving you the exact tools you need to absolutely crush your next technical coding interview. We're going to take a problem that looks kind of intimidating when you first see it on a whiteboard and break it down so clearly that you'll literally never forget how to solve it. Let's get into it.
Here's our quick roadmap. First, the symmetry problem itself. Second, finding the intuition. Third, the depth-first search solution. Fourth, analyzing the complexity. And fifth, a truly crucial interview tip you don't want to miss.
All right, part one, the symmetry problem.
So here is the absolute core of the challenge. How do you teach a computer to see a reflection? It's incredibly easy for the human eye to spot vertical symmetry, right? We just look at a shape, mentally draw an imaginary line right down the middle, and instantly know if both sides match. But, well, we aren't tested on our eyesight in a coding interview. We have to figure out the exact programmatic logic to make a computer see that a left subtree is a perfect mirror image of a right subtree.
And this brilliantly illustrates our ultimate goal. We want our algorithm to spit back true if the tree's left half perfectly mirrors its right half, right down that dotted center line. Just look at how the nodes with the value 2 mirror each other. Then, right below them, the outer nodes are both 1, while the inner nodes are both 4. That is exactly what vertical symmetry looks like in a data structure. It's almost like folding a piece of paper in half.
Moving on to part two, finding the intuition.
Okay, to really wrap our heads around this, we can metaphorically chop off the head of the tree. Notice how the root node, that 5 at the very top, is grayed out? The root itself actually doesn't affect the vertical symmetry at all. We just have the task of comparing the two subtrees below it to check if one vertically mirrors the other. Honestly, once you isolate the problem to simply comparing a left subtree to a right subtree, the whole thing instantly becomes way more manageable.
So how do we actually go about comparing them? Well, you might recall from the classic invert binary tree problem that an inversion means swapping the left and right children. And guess what? This is the exact same underlying logic. This tells us that a node's left child in the left subtree absolutely must match the value of the right child of the corresponding node in the right subtree, and vice versa. It's a literal mirror, meaning everything has to be perfectly flipped.
Which brings us to part 3, the depth-first search solution. So let's build this out. We start our DFS, our depth-first search, by taking the root of our left subtree, we'll call that node 1, and the root of our right subtree, node 2. Step 1 is pretty straightforward. We check if the values of these two nodes are equal. If both are 2, for example, node 1 val equals node 2 val is true. This establishes a solid baseline rule before we dive any deeper. Because if these root values don't match, there's no way the tree is symmetric, right? We just immediately return false and save ourselves the trouble. Now here is where the absolute magic of the algorithm happens. Since those first nodes are equal, we move forward by making 2 recursive DFS calls to do a sort of crisscross comparison. We check node 1's left child against node 2's right child. So we're comparing the outer edges. Then we check node 1's right child against node 2's left child, the inner edges. This crisscross perfectly simulates the physical act of mirroring. And the truly critical detail here is that both of these recursive calls must return true. It's a logical and condition. If both checks pass, our subtrees are symmetric, and we just keep repeating this crisscross process all the way down the tree.
But what about when things go wrong? During this entire traversal, the subtrees are immediately flagged as not symmetric if we hit one of 2 failure conditions. First, like we just said, if the values of any 2 compared nodes just aren't the same, obviously that's a fail. Second, and this is a structural failure, if at any point one of the child nodes being compared is null while the other one isn't. Think about it. A mirror can't reflect something that isn't even there. If one side has a branch and the other side is just empty space, the symmetry is totally broken.
All right, let's quickly hit part 4, analyzing the complexity.
Let's rapidly break down what this solution costs us in big O notation. Both time and space complexity are O of n. Time is O of n, where n is the total number of nodes, because our algorithm processes each node recursively at most one single time. We aren't wasting time doing any repetitive checking. Space complexity is also O of n. This is purely due to the space taken up by the recursive call stack running under the hood of your program. That stack can grow as large as the height of the binary tree. And in the absolute worst-case scenario, like, say, a completely unbalanced tree that just forms one long straight line, that height is n.
Finally, part 5, the crucial interview tip.
Seriously, if you only take away one single thing from this entire explainer, let it be this. Always cover your null cases before trying to access attributes. This is an absolute survival must in an interview setting. Always check for null or empty inputs before your main binary tree symmetry function tries to access left or right attributes. Look, in our DFS function, if you try to ask the computer for a node's left child's value and that node actually happens to be null, your code is going to crash hard, and your interview will get very awkward very fast. Handle those nulls first.
As we wrap this up, I really want to leave you with a thought to chew on. As you're prepping for that big technical interview, ask yourself, how could this mirror metaphor and this crisscross DFS logic unlock solutions for other complex tree structures you might encounter? Once you really grasp how to make a computer see a reflection, you start to realize just how beautifully flexible recursion can truly be. Thank you so much for joining me in this explainer. Keep practicing that crisscross logic, and seriously, best of luck on your next interview. You've got this.